Good day, folks. This is another chemical equilibrium question. It says hydrogen and iodine are sealed in a 2 cubic decimeter container. The reaction is allowed to reach equilibrium at 700 Kelvin according to the following balanced chemical equation. Here's the balanced chemical equation. It's a hydrogen gas react with iodine to produce the hydrogen iodide gas. Now 6.1, it says give reason why changes in pressure will have no effect on chemical equilibrium. The factors that affects the chemical equilibrium, remember, it's a concentration, it's pressure, it's temperature. But now pressure won't have any effect here in this chemical equilibrium. So it won't change the position of the chemical equilibrium. The reason is that if you look at this balanced reaction here, there's one mole of hydrogen gas and 1 mole of iodine gas in the reactant. That makes 2 moles of gas in the reactant, and in the product there's 2 mole of gas. Now 6.1, the reason is that the number of moles of gas particles in reactants is equal to the number of moles of gas particles in reactants, in products, right? Once the number of moles are equivalent in product and reactants, there will be no effect of chemical equilibrium position by pressure. Question 6.2, it says at equilibrium 0.028 mole of hydrogen gas and 0.017 of iodine gas are present at the container. So at equilibrium, those amounts of hydrogen and iodine are the amounts that have been remained after the equilibrium has been reached. So that's an axis, in other words. The question, it says calculate the initial mass of iodine gas in grams that was sealed in the container if Kc is 55.3 at 700 Kelvin. These amounts that remained after the equilibrium has reached, we can place them in the table which I've already drawn. The number of mole of hydrogen gas at equilibrium, we're going to place it here at 0.028, and the number of moles of an iodine gas, not there, sorry guys, I have to place it here, not there. These are the number of moles at equilibrium here, and the number of moles of iodine, it's 0.017 there. And now we do not know the concentration of the hydrogen iodide, which is the product. So what we can do, we can convert this number of moles at equilibrium into a concentration at equilibrium, because we're given the volume. So I will use the formula that says C is equal to N over V there, which is 0.028. We divide by the volume that we're given, which is 2. And here it's going to be 0.017. We divide by 2. So the answer there, it's going to be it's going to be 0.014 there, and this concentration, it's going to be 0.0085. That's the concentration there. Now that we have the concentrations at equilibrium and we have the Kc, that can assist us to calculate the concentration of the product, which is the hydrogen iodide, by using the Kc expression. We can go and say Kc is equal to the product, which is the hydrogen iodide, and there are 2 moles of hydrogen iodide. So we're going to have the square there and divide by the hydrogen gas, multiply by the iodine gas. They all have 1 mole there. So now let's substitute what we have. We're given the Kc value there. The Kc value there, it's 55.3. We'll substitute the 55.3, and the concentration of hydrogen iodide, which is the product, is the one that we're looking for. The concentration of the hydrogen gas is 0.014, and the concentration of the iodine is 0.085. And then we do the math there, and then the concentration of hydrogen iodide, when you get the answer of this product, you multiply by that, and then you put the square root, and then the concentration there, it will be 0.08112 mole per dm3. Do not forget the units when you are calculating this. And then we'll take this concentration and then we place it here, and then so that it can assist us to calculate the initial mass of iodine. So it's going to be 0.00112. I hope that you follow that, guys. Now the number of moles, we can convert this concentration into number of moles at equilibrium, because we are given the volume in which this reaction is taking place. Using the formula that says C is equal to N over V, we have the concentration and we have the volume. We'll cross multiply and then we'll get the number of moles. So basically we times by 2 there. So our answer there, it's going to be 0.08112 multiplied by 2. It's going to be 0.1622, right? Now the part that I like in this, or the easiest part there, and the change in the number of moles for hydrogen, since we have 1 mole there in the ratio, we're going to have minus x there. Okay, let me put it aside. It's going to be minus x there, and since we also have 1 mole of iodine there, we're going to have minus x there. And then for an hydrogen iodide, we're going to have a plus. Since it's a product, it's going to be plus 2x there, right? Now, since we are not given the product there, we'll put 0 there, right? Now, we are looking for the initial mole of hydrogen iodide in mass. We must keep that in mind. So what we're going to do here, the hydrogen iodide concentration at equilibrium will assist us to find these values. So what we're going to do here, we're going to do some little bit of maths. We will say 0 plus 2x. We take what is formed there and what has been formed there. So it's going to be 0 plus 2x is equivalent to 1622, and then we'll have 2x is equal to 1622, and then we divide by 2 both sides. Our x value there, it's going to be the half of that, it's going to be 0.08112, right? So that's the x. So our x, we substituted the x's there. So if we say 2 multiplied by 0.08112, the answer there, it will be the same value there. It will be 0.1622. That's the answer there. I hope you can see that, and the x we already calculated, so my x there, it's going to be 0.0112, and same as this side, 0.08112, right? Now we are one step ahead to the mass that we wanted, the initial amount of mass of iodine there. Now what we're going to do now, we're going to normally what we normally do, we say this initial amount minus the amount has reacted, and will give us what will remain there. So what we're going to do there, we'll say this value is x as well, but let me put it in a red color or in a white color so that you can see. So this is x. So what are we going to do there? We're going to do some little bit of math as well. So we'll say x minus 0.08112 is equivalent to 0.017. And then we transpose to this side, x will be, our x value there, it's going to be 0.017. 0.9812. That's the value, which is, these are the initial number of moles there. So this is the number of moles of what? Of iodine. These are the number of moles of iodine. Now we have to convert these number of moles of iodine into a mass by using the formula that says number of moles is equal to mass over molar mass. We take that, we substitute there. It's going to be 0.9812, and we want the mass. And iodine from the periodic table, the molar mass of iodine 2, from the periodic table, it's going to be the molar mass of the iodine. Let me quickly check in the periodic table. It's going to be 254, and then we cross multiply there. The mass of iodine, which is the initial mass of iodine, it's going to be 24.92 if you put that in the calculator. And then we are done with that question. I hope it makes sense and it's not haphazard. Right, let's move to the next question. Next question. The reaction rate versus time graph below shows different changes made to the chemical equilibrium mixture. Looking at the graph of reaction rate versus time, if you look at 0 minute there, at 0 minute, the both rate of forward and reverse are equivalent there. They're both equivalent there up until 2 minutes. At 2 minutes there, there's some disturbance there. That disturbance there, it tells us because both rate of forward and reverse increased both up until they reached equilibrium, or when the system reinstated the new equilibrium, it tells us that here there's an addition of what? Of catalyst, right? There's an addition of the catalyst. Remember, the catalyst is not one of the factors that affects the chemical equilibrium, because it increases both rate of reaction, most especially if you're adding the positive catalyst, right? And if you look at T4 there, there's a slight decrease in the reverse reaction there. If you look at the reverse reaction, there's a slight decrease there, and also there's a sharp decrease in the forward rate of reaction. So once there's a slight and a sharp decrease in both reactions, it tells us there that there's a what? There's a decrease in temperature. There's a decrease in temperature. So that decrease in temperature, it favors the what? The exothermic reaction. So, and another thing that is important that you need to look at there, the one that slightly decreased there, which is the reverse reaction has slightly decreased there, and the forward reaction has sharply decreased, which has decreased more. So the one that decreased less is the one that is favored. So the reverse reaction is favored there. So the favor there, it's an exo-reverse reaction, right? In other words, all the time when there's a decrease in temperature, the favor will be the exothermic reaction. So the exothermic reaction here is the reverse reaction. Now, the system reinstated the equilibrium at 6 minutes. Now let's look at 8 minutes. What happened at 8 minutes there? At 8 minutes there, there's a sharp decrease in the forward reaction rate there, but there's a slight decrease. There's a slight decrease in the reverse reaction there. But if you're looking at the one that has the sharp decrease, which is the forward reaction there, the forward reaction has a sharp decrease, and then what the system did, the system increased it. So possibilities, or the high possibilities here, there was a change in what? In concentration. But what change in concentration? We'll talk about that in the questions, right? Okay, let's look at the question 6.3 now. 6.3, it says, what do the parallel lines in the first 2 minutes indicate? These parallel lines in the first 2 minutes indicate that there is the chemical equilibrium that occurs there. Chemical equilibrium that occurs there. And 6.4, or in 6.3, you can say it indicates the rate of forward reaction that is equal to the rate of reverse reaction there. Now 6.4, it says state two possible changes that could be made to the reaction condition at T2. I already mentioned one, the addition of catalyst at T2 here. And another possibility there, it's what? It's an increase in pressure. There, it cannot be a temperature, it cannot be a concentration. It can be a what? A pressure there. But the definite one that has happened there, it's the addition of catalyst. 6.5, it says the temperature at equilibrium, the temperature of the equilibrium mixture was changed at a T4. As I've mentioned, at T4, there was a temperature change there. Now, 6.5.1, the question, it says, is the forward reaction exothermic or endothermic? Now, remember, I said there, the reverse there is what? Is exothermic. So the forward will be endothermic. 6 point, okay, it says fully explain. It says we must fully explain the answer there, why we arrived to that answer. So what are we going to say there to explain that? We will say the rate of forward reaction, decreased more, as I've mentioned there. If you notice there, the rate of forward has decreased more, and we can say there, and we can say the secondary thing that we can say there, decrease in temperature favors what? A decrease in temperature favors exothermic reaction. All the time. You got the 2 marks there. The 1 mark is for this, and the 2 mark is for those points that you have made there. Now let's go to 6.5.2. How will this change influence the Kc value? Guys, what do you need to remember? The only factor that influences the Kc value, it is the temperature. So in 6.5, there has been a decrease in temperature. So it doesn't mean that since there's a decrease in temperature, there will be a decrease in the Kc value. A decrease in temperature can be an increase in Kc value or a decrease in Kc value, right? But let's look at the Kc value is directly proportional to the concentration of product. But in this case, the product, our product there, it's the hydrogen iodide. Now, let's look at in this way. Now, if the forward reaction is favored, that means the concentration of product will increase and therefore the Kc will increase. But in this decrease of temperature here, it's the reverse reaction that is favored here. So if the reverse reaction is favored, that means the concentration of product will decrease and the Kc value will what? Will decrease. So the answer here, it will be decrease. The Kc value decreases because of the concentration of product decreases because it's the reverse reaction that is favored. 6.6. What change was made in the equilibrium mixture at 8 minutes? As I've mentioned, at 8 minutes, there was a change in concentration, right? A change in concentration. But what change in concentration? There was a removal, or there was a decrease in concentration of the reactants. How do I see that there was a decrease in the concentration in one of the reactants? Because if you look in the rate of reverse, the rate of forward, the rate of forward has decreased, which was the disturbance, right? The rate of forward has decreased, but what happened to it? The system increased it. So if the system increased the rate of forward, there, that means has increased the rate of forward there, that means that there was a decrease in the reactants. Let me show you this quickly. So this is what happened. If you decrease here, or one of the if you decrease one of the reactants here, what's the system is going to do? the system is going to oppose what you have done, is going to increase the concentration of the hydrogen, and also increase the concentration of iodine. And what is going to do the system in the product is going to decrease the concentration of the product. So the favor here is going to be what? A reverse. The system will favor the reverse reaction, right? Will favor the reverse reaction. So now, how do we see it there here? It's because if you look at these curve at 8 minute, what is favored here? The one that is favored is the one that slightly decreased, which is the reverse. And here, the rate of forward has decreased and the system increased it, right? So the answer here, it's the removal or decrease in concentration of iodine, or the concentration of hydrogen gas, or we can say the concentration of reactants there.